All right. Thank you all for joining us. Welcome to our next 2020 STEM Education Speaker Series. Today we have Miss Lindsey Clark. Lindsey Clark is a first-generation college student from Mobile, Alabama. She is finishing her master's degree at the University of South Alabama in the Brain and Behavioral Sciences program. She met my colleague and friend, Dr. Jack Shelley Tremblay, Dr. ST, in 2017, and has worked as our research assistant on a grant generously funded by the W.K. Kellogg Foundation for the past 2 years. As part of that work, she has conducted multifaceted structured interviews with over 50 preschool-age children, presented findings at the Southeastern Psychological Association annual conference, and was awarded the title of Outstanding Student in Psychology by the South Alabama faculty in 2019. She successfully defended her master's thesis last week and is currently pursuing doctoral programs to continue studying embodied cognition, mathematical reasoning, and childhood development. Please help me welcome Ms. Lindsey Clark to the Center for Science and Mathematics Education here at Southern Miss. And normally we would clap and we would shake your hand, and so welcome, Lindsey.
Thank you. Thank you all for tuning in. Yeah, the title of my thesis, and this is what I'm mostly going to be talking about, is the development of a new task to assess shared developmental trajectories for fractional reasoning and fine motor ability in 4- and 5-year-olds. So some of our research questions for this study were, are preschool-age children capable of understanding and solving fractional quantities? Is fine motor ability correlated with mathematical achievement and the use of counting gestures in preschool-age children? And also, what is the role of gesture in counting? So our background, so our IRB was from the University of Southern Mississippi, and it's a collaboration with Dr. Julie Swickla. And she went over, our grant was from the W.K. Kellogg Foundation, titled Interdisciplinary Mathematics and Literacy E-Stories for Young Learners, Math Sharing Stories. So for our literature review, I'm going to talk about mathematical cognition, fair sharing, fine motor ability, and gestures. And I feel like to talk about the development of numerical and arithmetical skills, we need to talk about number sense, fluid intelligence, working memory, and our approximate number sense. So first I'm going to jump into number sense, and that is our innate cognitive ability to quickly recognize, approximate, and manipulate numerical quantities. So this allows us to use numbers as a fundamental parameter by which we make sense of our world. So there's evidence for a dedicated neural system for number sense. In the inferior parietal region has been identified to be a significant node in the circuit of the number sense system because it displays activation while an individual performs various number processing tasks. And consequentially, damage to this area can result in impaired internal representations of quantity and an inability to comprehend the actual meaning of numbers. And also, while we're very young, fluid intelligence has a very big role in our cognitive development. And that's the use of deliberate and controlled mental operations to solve novel problems. So this allows us to use inductive and deductive reasoning to draw inferences, conceptualize information, test and generate hypotheses, identify relations, solve problems, things like that. And it's also a predictor of mathematical achievement in children. And this could partly be explained by the higher order cognitive abilities that fluid intelligence provides us with that in turn aid in mathematical reasoning, because it allows us to understand mathematical concepts by forming these abstract representations of quantitative and qualitative associations between variables. And the study by Premi et al. Had a study with kindergartners, and they hypothesized that success in learning math requires fluid intelligence. And they found that students who scored higher on their fluid intelligence measure displayed a more rapid increase in math scores over the span of 2 years than did students with lower scores in fluid intelligence. So the approximate number sense is an extension of just the number sense, and Wang et al. Described it as a theory to describe how we understand symbolic, so that's Arabic numerals, number words, and non-symbolic, so unrelated dot patterns, random stick patterns of numbers. So this is also, composed of the innate systems that allow humans to represent numerosities. And it allows us to recognize the magnitude of both symbolic and non-symbolic numbers. So these ANS representations, like the word 5, F-I-V-E, and the Arabic numeral 5 are mapped onto extant symbolic representations, thus reinforcing the strength between Arabic numerals and number words through language. And that's the reason why it's so important during this developmental period with preschoolers, 4 and 5-year-olds, because they're beginning to use language in a more meaningful way. So the study by Gimber et al. Found that ANS acuity was a significant predictor of mathematics achievement at 5 years of age, but not at 7 years of age. So quickly refer back to that fluid intelligence measure, they found something very similar as well. And they suggest that a reason for this is that as mathematical thinking advances, children begin to rely less on their ANS and more on other cognitive mechanisms. And the results from the study indicate that after the ANS relationship is formed, working memory assumes a larger role in mathematical reasoning. So we describe mathematical working memory as a mental workspace necessary for controlling, regulating, and actively managing information necessary to complete complex cognitive tasks. So the study by Gimber et al. Highlighted the transitional period between the ages of 5 and 7, where the brain seems to be switching gears in a way from relying on ANS to working memory. So they suggest that a reason because of this is after we learn the magnitude of numbers, we then learn how to manipulate them and work with them while keeping in mind these rules of arithmetic. So the difference shown between these ages suggests that there's specific developmental processes and important changes in cognition that are happening, which can potentially predict an individual's success in learning mathematics. So these cognitive and metacognitive processes, like effectively processing, diagramming, and solving multi-step mathematic problems, are apparent when working with numbers. This is significant because deficits in working memory, so problems with managing, storing, and integrating information for more than one step, are common in children with learning disorders. And it's important in the classroom as well because behaviors that facilitate learning, so like following direction and sustaining attention, are the basis of succeeding in a traditional school setting. All right, so also with numerical cognition, the Wang article described 2 types, numerical abstraction, which allows the individual to form mental representations of numbers. And there are 2 kinds. So subitizing, which is pretty much you can look at a set of dots or anything and immediately know how many they are. So this is rapid, precise, accurate, and we use it when counting generally less than 4 items. So counting is more error prone, it takes longer to process, and typically developing children as young as 3 years old have an understanding of small numerosities, so up to 4 items, and understand that counting is a way to find the total number of items in a set, which is what we call the cardinality. Cardinality. Numerical reasoning is the set of cognitive abilities that are used to mentally manipulate representations of numerosity. So this gives us a sense of a numerospatial mental number line that helps us manipulate and calculate numbers in our head. So this is an important tool, especially when we begin to learn fractions, because it helps us understand that all numbers have specific magnitudes that can be located on a number line. And because our knowledge of fractions begins with a whole number bias that we learn through counting and sharing, the use of language can help us conceptualize numbers on a more abstract level by expanding the semantic range of the concept of number. So fractional reasoning is important because it's also relevant to higher levels of mathematics learned after fractions, like algebra and trigonometry. And understanding fraction magnitudes is central to numerical development because fractions allow children to understand, to deepen their understanding of numbers beyond the level likely to arise with experience from whole numbers only. And in turn, the mental number line, it provides this integrated spatial structure necessary to represent both whole numbers and fractions. And like I said, it helps children see that there's an infinite number of fractions lying between whole numbers. And learning activities that emphasize the number magnitude understanding may be the most beneficial method to teaching fraction concepts. And research on the neural and cognitive mechanisms behind numerical reasoning and fractional reasoning is instructive to education research because an insufficient foundational knowledge of numerosities, like place value, addition, and subtraction, may lead to difficulties with mathematics in later years. Yep. So numerical cognition also plays a role in sharing behaviors. So tasks that like source redistribution, the resource distribution, require the coordination of advanced behavioral and cognitive abilities that some researchers say may not be completely established yet in 4 and 5 years old. So we describe fair sharing as the ability to share items in a way that agrees with standard principles of justice. And our understanding of fairness, equivalence, and generosity may be a result of numerical cognition. And pre-K children may still be developing the cognitive abilities that enable them to behave in accordance with social expectancies. So this leads us into the study by Dr. Swickla in 2014, Can Kindergartners Do Fractions? And she investigated young children's naive understanding of fairness and sharing, and also differences in strategies using for solving contextual problems before the children had any formal instruction in school, and also whether these problems are best presented in the context of fair sharing. So she used snack sharing as a theme that children might find that they might recognize. And she found that children this age, because they are likely sharing and partitioning snacks and toys amongst their siblings and peer groups. And she found that preschool age children, so I believe it was 3 to 6 year olds, showed this intuitive understanding of fractional quantity and understand these notions before they start school. And also that preschool age children have the ability to consider, illustrate, and explain fair sharing tasks with mixed fraction solutions. So fine motor ability is the ability to synchronize hand and finger movements with the eyes. So this is activities like drawing, writing, and grasping a pencil. And it's controlled by the cerebral cortex, the basal ganglia, the cerebellum. And these areas are often associated with mechanisms of executive functions like working memory, general reasoning skills, and attention. There was a study of a kindergarten classroom that found that 46% of the kindergartner's day is devoted to fine motor activities. And these activities would be something like writing, using scissors to cut paper, counting beans, or playing with toys like Legos. And this leads us into the use of gestures. So they help people with activities like speaking, counting, learning, and problem solving. And students routinely gesture whenever they talk about mathematical concepts because gesture supports accuracy in areas of mathematics like counting and solving equations. It can help gesturing during math instruction can help students better retain concepts because it can contribute representational supplemental information that may not be conveyed by verbal language alone. Gesture also aids in solving accuracy of children whose mathematic problem skills are still in a state of development. And because we learn how to count typically using our fingers when we get into preschool and kindergarten, these finger-based instructions provide the preliminary access to foundational mathematical concepts like one-to-one correspondences and part-whole relations early in development. So for this study, there's a ton of gestures. So for this study, we're just looking at 4 different kinds of gestures. So, well, just 3 actually: accuracy, synchrony, and morphology. And then we added in subitizing as well, because we are doing a dot counting task that I will get into in just a moment. So fine motor ability and cognitive development are not as separate as traditionally thought. So there's evidence that they're fundamentally intertwined and that they display equally protracted time courses during development. And because most activities that demonstrate because the same brain structures are used during mathematical and motor activities. And this is important for school readiness. And also children may benefit from gesturing because it activates these cortical regions that underlie numerical cognition, particularly counting. And that's because we learn how to count on our fingers, which reinforces these associations. So our current study, we had 3 hypotheses. My first was that I predict a similar result from Swickla 2014 in that preschool age children have the ability to conceptualize and solve simple fractions. My second hypothesis was that I predict to see a positive correlation between fine motor ability and performance on the mathematics task. And my third was that I predict gesture ability will correlate with measures on our mathematics task and with performance on the groove pegboard task, which is my test of fine motor ability. So participants included 33 children aged 4 to 5 in a Southeastern public school. And the children were examined individually by me in a private interview-like setting within the school. I would pull them out of class one by one. It would take between 30 and 45 minutes for each child. The first thing that they would do is these math stories, and they were presented as pictures of items on paper, and I asked them to portion the items evenly and fairly amongst people or other objects. So after the math stories, the children completed a dot counting task where I get them to gesture while counting dots. And then after the counting test, the children completed the groove pegboard test, and they did 2 trials with that, dominant hand and non-dominant hand. Yes. So these math sharing stories are based off of Dr. Swickla's 2014 study, and they evaluate children's ability to understand and solve fractional quantities involving wholes and 1/2 fractions using equal sharing. So this was a paper and pencil format, and there were 9 questions. And this is an example. I would say something like, here we have 4 batteries and 2 robots. Can you split up all the batteries so that each robot gets the same amount? And this is examples of 2 children's work. So this child right here obviously did it wrong, and this one did it right. At one point I did have their scores on my fine motor ability measure, but I need to go back and find those because that was interesting. The child that did not solve this well took a lot longer to do our fine motor task. I don't think videos play, but right? Okay. This is just an example of the pictures, and I would get them to draw. There's actually 2 cartoon kids, and they would draw and talk about how they would distribute the items.
If you push the play button, it will play.
Will it?
Yeah. Mm-hmm.
I thought it didn't. Oh, it does. Can y'all hear it?
Yep.
Oh, okay.
4? Yep. Cool. Well, I'm going to give you a sheet of paper with some questions on it, and I'm going to read the question to you about sharing, okay? So what does it mean to share something fairly?
I don't know.
Yeah? That's fine. Well, to me, sharing something fairly means that everybody gets the same amount, okay? So,
I'm naughty.
okay. So I'm going to do the first 2. Okay. Looks to me like we put 1 key in that lock, right?
Yes.
And how many keys do we put in that lock?
1.
Okay. So let's go on to the next one.
Yeah. Hey, robots are my favorite.
Yeah, robots are my favorite too. So here we have 2 robots, 1, 2, and 4 batteries. 1, 2, 3, 4. So help me split up all the batteries so that each robot gets the same amount, okay?
Hey, robot right there.
Okay.
I put an X.
No, well, we can, okay.
You see, I let them pretty much do what they want. I don't really correct them very much, but then he gets it, I guess. Yeah, so that's all I wanted to show you all with that. The groove pegboard test, it measures both motor speed and hand-eye coordination, and it requires manual dexterity for completion. So there are the individuals tasked with inserting all 25 pegs into the holes in the pegboard one at a time, and their score is determined by the amount of time taken to complete all of the rows and the number of peg drops. And this is just a quick video.
All right, so this is the groove pegboard test. It's placed in middle, and you work your way this way, and each row you start back at the same side.
See, all the holes are kind of oriented differently, so they really need to have this
row completely from this side to this.
This precise pincer grip that allows them to twist and fit the pegs into the holes. I found that some children around in preschool are using a fist grip rather than like what you would use to hold a pencil. So those children often struggled with this. So the dot counting task, the participants were told to count the dots in one box at a time out loud and using their finger. So they would start here at these at the 2 and then go right and then down and then here, and I would prompt them for each card. We created this behavioral rating of gesture looking at accuracy, synchrony, and morphology, and also whether or not they supertise. So they were able to look at this first card and see that there are 2 dots and immediately say 2. But they weren't explicitly told to supertise. Here's our scoring system. For example, for morphology, we really wanted to see this formed hand, tucked fingers, and a single pointing digit. So that would get a 3. For accuracy, that is just the number of gestures that they made. So if they made 2 gestures to count 2 dots, then they would have gotten full credit on that. And synchrony can be thought of as gestures and the correct number spoken. So we explained accuracy as the discrepancy between the number of gestural points and the actual number of items on the card. Synchrony is how well does the gesture synchronize with speech, and morphology, like I said, we're looking at that formed hand with tucked fingers and a single pointing digit. So here are some results. So in order to test hypothesis 1, which that preschool age children have the ability to conceptualize and solve simple fractions, we performed a descriptive analysis on the mathematics story's total scores. We found a mean of 40.36, and that divided by 76 means that children scored an average of 53.11% correct on average. But in order to determine if the children performed better than chance, an a priori baseline probability of mathematics total score was calculated. And each of the 9 items had different probabilities of achieving a correct answer if the children were simply guessing. So for instance, for the first one, there are 3 locks, which represent a priori A category, and 3 keys, which represent a priori B. In this example, the multiplicative combination of both a priori events getting the correct answer was 10.89% correct. And then the a priori baseline probability of all the math stories scores was computed to be 12.46. So we put that into, we made that our test value for a t-test, which also gave us a significant value. In order to test hypothesis 2, which that we'd see a positive correlation between fine motor ability and performance on the mathematics task, we did a correlation. And we found that mathematics total score correlated significantly with pegboard dominant hand time, non-dominant hand time, and non-dominant hand drops. So we did a linear regression to see which variable explains most of the variance, and we found that the non-dominant yields the non-dominant drops yielded an adjusted R² of 0.234, indicating that the number of non-dominant hand peg drops explains 25.8% of the variance of the dependent variable, which was mathematics story total score. So whenever we exclude non-dominant drops, the linear regression found that no other pegboard variables correlated as significantly with mathematics performance. So here's a scatterplot of our regression with our R² as 0.258. And in order to test hypothesis 3, which that gesture would correlate with mathematics total score and performance on the pegboard task, we first did a test of normality to check for any violations of normality within the gesture variables. So we did find that it was pretty heavily kurtotic and skewed. So we did a Z transform on those variables. And we found that math story score correlated significantly with subitizing and accuracy, but not hand morphology or synchrony. And this is a scatter plot of accuracy and accuracy of gestures and mathematics performance with a correlation of 0.23. Okay. And in order to look at pegboard performance and the gesture variables, we did another correlation and found that accuracy was the most significant correlate of the group pegboard values with a P of 0.002, and for both non-dominant hand and non-dominant hand time, but produced insignificant values for dominant hand drops and non-dominant hand drops. So synchrony only correlated with dominant hand time, and hand morphology and subitizing produced no significant p-values for the group pegboard variables. So going back to our hypothesis, this was supported. Children indeed demonstrated the capability to comprehend fraction concepts, particularly within the context of fair sharing and division of items amongst people or objects. Because the children in our sample answer these problems correctly over half the time. Our hypothesis 2 was also supported. So correlations in a linear regression indicated that fine motor ability, as expressed by the growth pegboard, non-dominant hand time, dominant hand time, and number of peg drops by the non-dominant hand significantly correlated with performance on our mathematics task. Our third hypothesis was partially supported. So the regression showed that our gesture variables, accuracy and synchrony only correlated significantly with the growth pegboard test variables. And also that subitizing and accuracy were the only gesture variables that significantly correlated with mathematics story's total score. So I always like to put in a why is this important slide in my presentations. And I feel that children may benefit from gesturing during mathematics instruction. Also that the ability to solve fractional quantities is a critical cognitive milestone as it underlines the notion of fairness and equal sharing between one or more parties. So this leads me to wonder, should children be taught fractions before entering 3rd grade? Perhaps if delayed too long, the whole number bias may become the predominant scheme to which fraction language and symbolism is related. And preschoolers whose math skills are less advanced may benefit spontaneously from gesturing and explicit instruction to implement specific gestures because they may support counting to determine combine items and sets and determine sums. I feel that these findings are beneficial to strengthening the fields of childhood mathematics education, cognitive science, developmental psychology, even clinical psychology, and that it can also help with a possible future development of a standardized and structured fractional reasoning protocol. So we have a lot of exciting things going on with this study. So we're already got a class and a half finished with the e-stories. So these are the same questions using the paper and pencil format, are on a touchscreen e-story format. And I sit down with them and I record their time taken to complete each question and how many times they have to, how many attempts it takes them. We also are trying to get some eye tracking data to see where at and how long the child is looking at the computer screen while completing the e-stories. We've had some success with using a Wii balance board to measure gross motor skills like balance coordination, because those are actually correlated with academic performance as well. We're also doing hand movement tracking and we plan to quantitatively capture gestures for problem solving and supervising. These future analysis, we're talking about doing a rating of gestural complexity by using a fractal analysis. Also, we're doing, every child gets this socialization questionnaire, which asks about friendships and social emotional status within the classroom. And we also had physical manipulatives, 3D printed. So they're the same questions as the paper and pencil and e-story formats, but they'll actually be cutting a string and putting actual batteries into robots. So I'm pretty excited for that as well. All right. Thank you so much. Does anyone have a question?
Lindsey, thank you so much. That was great. If you all want to ask questions individually, please do that. Or if there are things you want to just type into the chat, either way. I see Jack giving you an applause, so that's good.
How do
I will ask you a question, Lindsey, based on what we talked about last week in your defense. I found the finding that the non-dominant hand relationship is very interesting. So can you maybe just give us a little bit of insight or other thoughts you might have on that relationship that you found?
Yeah, so I really don't know why non-dominant hand would correlate the most. I do know that children around this age are switching which hand they choose to be their dominant hand often. So maybe that has a little bit to do with it. Maybe it has to do with these neural systems and the way that they communicate throughout the brain. Really not that sure, but I'd be very interested in exploring that.
Lindsey, great talk.
Thank you.
This is Dr. Howell speaking for everybody else who doesn't know me. I have a question about some of the conditions that you had, or the experiment itself. In adult populations, typically in embodied cognition tasks having to do with gestures, they do have a control condition where they compare no gesturing with gesturing in cognitive tasks. Obviously, it would be immensely difficult to institute a control condition for 4- and 5-year-olds. Mm-hmm. But can you give some maybe prediction about how they would react to it and how their performance would be?
I think that they would not like that at all. I think that around this age, children are, it's really being emphasized to use your fingers when you're counting. So I feel like the children would perform worse because maybe it's a compensatory method that they're using because they don't have these, foundations of, arithmetic and mathematical reasoning solid. So I think gesture aids in that.
And I'm not a teacher, but as a follow-up, but I noticed just over the years of educating our kids is that as they age, the teachers are more and more discouraging them from using gesturing for math problems. And I was wondering if that's some sort of a policy of in educational training. Is it a tool that that the teachers are trained with, or something else, or it's just spontaneous?
Well, I don't really know the answer to that, but I do remember teachers literally saying to sit on your hands, or just don't, like, they do not want to see you using your fingers while doing math. So maybe Dr. Slicklip could better answer that question, because I'm not very sure how, you know, the teachers, like what explicitly they're told.
Right. So it's, yeah, it's a little bit of a historical norm of having kids behave, right? I always tell all of my teachers and all my students, no matter what standardized test you go into, hopefully you'll have 10 of these to bring with you. So use them as much as you can. These are your manipulatives that you have with you all the time. So why not use them? You know, obviously professional speakers tried not to use their hands too much. So I think there are ways that we, you know, can think about gesturing and controlling those gestures. But certainly for this age child, I think it's, you know, I think it's a very, very interesting. We actually there's a couple comments in the chat. Rachel saying she wonders if it's a social norm, and from Jennifer, I think it's an older style of teaching. I teach high school math, encourage students to use whatever methods they need. Yeah, if their fingers are helpful, use them. Exactly. Why not? One quick example though, too, to add to your question, Alan. Jack, if you'll remember, we had a doc student not that long ago who was also looking at gesture. And she did create a experimental design where she had children put their hands into gloves. And we were trying to come up with a way to have students solve without gesturing and look at those types of conditions. So she had gloves attached to a wooden board. So the students actually were not restrained per se, but they were not allowed to use their hands. And so Golden Meadow's work leads a lot of that. And so it was very interesting to sort of see how gesture extends the way students are able to explain their answers, and how constraining that can really be of distraction, especially for this very young age child. I mean, nobody wants to have their hands restrained. Really.
Well, I think one of the things that's potentially really interesting is to look at the idea that there's a rush to move children into an abstract problem-solving frame. When you use your fingers, you embody the math problem. And you are the manipulative, if you will, in that situation. And you can take that set of quantities, represent it somehow in your own action space, your own somatic representation of what you're trying to solve. And I think that's extremely powerful for children that don't have the full adult set of working memory functions totally online yet, because it really provides tremendous savings for their working memory to have those quantities represented on their digits. And so I'm really interested in that notion of the self-referential versus the object or conceptual referential frames for problem solving and what those implications are.
And if I may add to it, in the adult gesture and embodied cognition literature, there's a nice metaphor that describes these effects, which, by the way, are present still in adults. Is that it seems to be the case that gestures are sort of greasing the wheels of cognition. That is one phrase that has been used by many publications. And the gesture doesn't even have to be task specific. It could be just something that you do, like I'm doing right now, right? It's not specific, but I'm bringing out the words, and gesturing helps, both with, you know, verbal utterances and thought processes.
Yeah, I've read quite a bit of literature showing that it decreases the cognitive load, which helps you better actively manage other tasks and multitask, I guess.
By the way, head nodding is also a gesture, which is what we do.
It's hard. It's a little harder to count with your head, I guess. But you can do it. You can do it.
You can.
True.
Oh, interesting comment just came up. Julie, did you see that one?
Yes, I'm reading that from Lewis, is one of our new math at master's students. Teaching 6th grade students, I try to encourage students to begin relying more on instant recall instead of using your factors for 2 reasons. Obviously, it takes longer. We are timed on the Mississippi test, which our schools are rated on A or B. If they bog down in finding an answer by using fingers, which should be readily available using recall, then it inhibits their ability to concentrate on more advanced problems. Right. So, I mean, you know, and this kind of goes hand in hand with the subitizing, right? So if you can subitize 4, you don't have to count 4 and then hold those up and reserve that, you know, cognitive load over here. So there are places where at some point, hopefully these things are routinized. But you know, it's a hard balance. And I'm sure, Lewis, you see that with, you know, at middle grade students are still struggling with their multiplication facts and all of that. So yeah, it's hard to ungesture, but at some point, hopefully those become more routine.
This is especially interesting, I think, for cases with learning disability. You know, students who have learning disability might have a hard time suppressing their gesturing because they might have processing issues in terms of memory or just rote memorization, and they're compensating it with gestures. So maybe that's a sign of learning disability or some inkling of it.
There's a small thing too. I don't want to hog the talk, but in terms of our finding of the non-dominant hand being more predictive of mathematical ability, what Dr. Heinall said reminds me of one possible interpretation, which is that oftentimes in students with learning disabilities, you see that their left-right differentiation is behind, and you have folks who are a little bit more ambidextrous longer in folks with learning disabilities, and that sort of that right hand, strong right-handed differentiation, or in lefties, strong left-handed differentiation, is part of normal maturation. So when I look at the correlations, they seem to be driven by the scores on the low end as opposed to the middle or the high end. And so it does seem like our students with delays are driving the correlation such that if they tend to have these slower scores on the non-dominant side, they tend to also do more poorly on the math stories.
Excellent, excellent. Any more questions for Lindsey? So appreciate your time. It's so nice to see you all. I miss you all, seeing you all in person for sure. So, and I know that Kendrick will be assigning on, I'm sure, a nice reflection for our graduate students on this talk as well. And please feel free to contact Lindsey or contact me if you have any other questions or other thoughts about this. Jack, Lindsey, and I are all really excited about this work and seeing where we can continue taking it. So, Lindsey, thanks for doing a great job today. You rock.
Thank you for inviting me. Thank you for everyone that showed up.
Sure. All right. Take care, all.
This is great.